Now we are going to start with the Bode plots. Before we discuss Bode plots, we will talk about the semi-log graph. How to plot a semi-log graph. Normally what happens in a normal graph, there is going to be x and y axis, right? And there are going to be divisions at equal intervals in both the x and y axis. Okay. Now what will happen in a semi-log graph? Here one axis will be in log scale, another axis is going to be a normal scale. That is why it is called semi-log. It is not completely logarithmic. Okay. So here what we do is the y axis we take as a normal graph and the x axis we take as the log scale. This is normal or uniform scale. Uniform scale is more appropriate because the readings are separated in uniform intervals. Okay. What do we usually plot on the log scale is the frequency. Okay. So the purpose of a semi-log graph is that we can get the whatever we are plotting on the y scale, be it the magnitude or the phase, we want its variation over a long range of frequency. You will get a long range. Okay. So why is that? Let us say at this point the frequency is omega 1, not 0, but we are taking as omega 1. Now the next reading will be 10 times omega 1 and the next reading is going to be 10 square times omega 1 and again 10 cube times omega 1. It is going to continue like that as a factor of power. It will keep on increasing with each reading. Okay. And in between there is going to be smaller readings as well. They are not going to be uniform. Slowly they are going to increase in magnitude. Okay. So there are going to be 10 readings. Now how will those 10 readings be? If you take omega 1 is equal to 0.1, then 10 times omega will become 1 radian per second. So the in between readings, they will be like 0.2, 0.3, 0.4 and so on till 1. Okay. So let us draw this on a separate scale so that it will become more clear to you. Let us say this is omega 1 is equal to 0.1. Next reading is going to be a little closer, which is 0.2. Next is going to be a little farther. This is going to be 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and finally what is the last thing that you're going to get? 10 times omega 1, which is 1 radian per second. Okay. So I have redrawn it again to show you that this in between the two major readings, the scale is non-uniform because it is a log scale. Okay. Now what about the other range? If you see, if this is 1 radian per second, this is going to be 10 square into 0.1, which is 10. Okay. So how the readings will go about here? 1, it will start from 1, then 2 will be there, 3 and so on till 10. And once again, if it is from 10 to 100, then it is going to be starting from 10, then 20 will come, 30, 40 and so on till 100. Okay. So in this way, you can see that within 3 major readings, we will be able to get from omega is equal to 0.1 to omega is equal to 100 radian per second. Right. But if you take a uniform scale, then what will happen? You're not going to get as many readings. So that is why in order to find out the range of y for a larger range of frequency, we use the semi-log graph. Now each of this major reading, it is called as a decade. You can see that each decade, if you compare, it is increasing by a factor of 10. Now there is another type of semi-log graph that we have, which is in terms of octave. Here we have seen in terms of decade because in each cycle the frequency is increasing by a factor of 10, right? Omega 1 will be at 1 range, then 10 omega 1, then 10 square omega 1 and so on. Now what happens in an octave is it will be increased by a factor of 2. Okay. So that means if this is omega 1, then this is going to be 2 times omega 1. This is going to be 2 square times omega 1 and in between the readings they will be equally divided, but the scale will be non-uniform. Okay. Now what will be the equation of a straight line in a semi-log sheet? So it will be useful later on, since it is a basic thing we are discussing right now, but the application you will see later on. Okay. So we know that the equation of a normal line we write as y is equal to mx plus c. This is on a normal Cartesian graph. That is, both the axes have uniform scale. Okay. But in a semi-log sheet, what is happening? The x-axis is a log scale. So we simply write y is equal to m. Instead of x, we write as log x plus c. Okay. So what is m here? This is a change of y over one cycle or one log cycle of x. Okay. Now if you take the base as 10, then we call it as a decade. If you take the base as 2, then we call it as a octave. Okay. So then change of y over one decade of x will be present if the base is taken as 10. If the base is taken as 2, then you say change of y over an octave of x. Okay. So that is how it is going to be. Then what about the value of c? The c is not the intercept exactly. It is more appropriately, it is the value corresponding value of y corresponding to the value x is equal to 1, right? Because only when x is equal to 1, this term will become 0 and c will be equal to y. Alright. Here what is c in a normal Cartesian graph? C is going to be the intercept with the y-axis. That means when x is equal to 0, the value of y will be equal to c. But here the value of y when x is equal to 1, that is equal to the c. Now we can start with the actual discussion of Bode plot. Okay. So how to construct a Bode plot? Construction of Bode plot. The Bode plot is going to consist of a magnitude plot, which is going to be a plot of magnitude on the y-axis, and on the x-axis it is going to be frequency. Okay. So this is the magnitude plot, and phase plot is similarly on the y-axis. Instead of magnitude there is going to be phase, and here it is going to be omega. This is log scale. Okay. The combination of both of these together, that is the magnitude plot and the phase plot together, they are called as the Bode plot. So what we need? We need the expression for whenever a transfer function is given, we will be needing the expression of the magnitude and the expression of phase in terms of the frequency. Now if you consider a transfer function, let us say g of s, this will be having some zeros, let us say s plus z1, s plus z2 and so on, divided by, we can take some poles at the origin and there will be some poles. Alright. Now what will be the first step? We will have to express in terms of the frequency, right? So what will be g of j omega? Wherever there is s, you substitute with j omega. Okay. So don't worry about the exact function. This is just for the sake of explanation. When we take an actual example, it will become more clear to you. Here I am just giving you an introduction. And here there is going to be the poles. Okay, so this is 3, right? Now what happens? You will have to take the magnitude, then g of j omega will be equal to, you can take the magnitude of each term, right? So the magnitude of the first pole, first 0, and into the magnitude of the second 0, and once again in the denominator also it is going to be mod of j omega to the power k, mod of j omega plus p1, mod of j omega plus p2, and mod of j omega plus p3, so on, whatever the terms are present. But we want the magnitude in terms of the dB, decibel. Alright. So what will be in terms of dB? It is going to be 20 log g of j omega. Okay. So then what will you get? Each of the terms which are being multiplied you can write as addition, and whatever are in the denominator you can write as subtraction, right? So that is 20 log j omega plus z1 mod plus 20 log mod of j omega plus z2 minus 20 log j omega to the power k minus 20 log j omega plus p1 minus 20 log j omega plus p2, right? So this is the magnitude. From here, what is the important observation that you can get is the total magnitude in dB is equal to the magnitudes or the sum of magnitudes of each term in the numerator. First you will add all of the terms in the numerator minus the sum of magnitudes of each term in the denominator. Okay. Or you can also write, if you take minus 20 log j omega plus p1 as one term, then what you can write? You can write as plus of minus 20 log j omega p1. Similarly, here you can write plus of minus 20 j omega to the power k. Okay. So you can write here the total magnitude in dB. Not only can it be expressed in terms of this term, that is sum of magnitudes in the numerator minus sum of magnitudes in the denominator, but you can simply write sum of magnitudes of each term. Okay, forget about numerator and denominator. That is because the minus that is coming because of the denominator we are taking into the bracket itself. Okay, so we can say that this is a 0, this term corresponds to a 0, minus 20 log j omega plus p1 corresponds to a pole. So if you add the magnitudes of the 0 and the pole, then you will get the total magnitude. Okay, so that is why this is a more appropriate term. So what we need to do? We need to find out what is the individual magnitude plots of a 0 or a 0 at the pole or a time delay function, and then we can just add up all of them and it will give you the total magnitude. Now what about the phase? The phase is even straightforward, right? How do we find out the phase? This is the sum of phases of each term in numerator minus sum of phase of each term in the denominator, right? So here also the total phase plot also you can write as sum of phase plots of each term. Okay. So what we will do now is we will take a simple function and we will find out what is the magnitude and the phase plots of that function, and then we will take the example of a function which is having multiple terms. Okay, and then we can construct the Bode plot of that function. First we will take a constant, a real constant, that is it does not have any imaginary part. Let us say that function is k. Okay, so that means g of j omega is equal to k. Then what will be the magnitude? Magnitude is simply going to be that constant k. And what about the phase? Phase g of j omega is going to be equal to 0 degrees if k is greater than 0. If it is less than 0, it means it is a negative real axis. Then what is it going to be? 180 degrees. This is if k is less than 0. So as an example, let us take g of j omega is equal to 10. Okay, then what will be the magnitude in dB? This is going to be 20 log mod g of j omega. This is going to be simply 20, because log 10 to the base, when nothing is mentioned, it is 10 only. We are using the log to the base 10, right? So this is going to be 20. Now what if this is equal to minus 10? If g of j omega is equal to minus 10, then also it will be 20 only, because this is only a magnitude plot. Remember that. Okay. Then what about the phase? The phase is given by 0 degrees. So you can draw the magnitude plot. This is frequency and this is the magnitude in dB. In dB is important. Okay. So let us say here we have minus 10, 0, 10, 20. So this is where the magnitude plot is going to be. This is for k is equal to 10. If k is equal to minus 10, then also this is only the magnitude plot, or k is equal to minus 10. What about the phase plot? Phase plot, see here I am not taking 0 at the origin, at the intersection of the two axes. So that means basically this is not the origin. Okay, so we are just trying to represent g of j omega as a function of omega. Don't take this as the origin. Even the frequency, we do not take 0, because we take the log scale. If you take this part as 0, then what will happen? The next part will be 10 times of 0, which will be 0. So usually we start with 0.1 or 0.01, the smallest frequency possible. Alright. Now what about the phase plot? Here the phase axis and this is the omega axis. Now 0 somewhere, if it is here, then this is going to be the phase of g of j omega is equal to 10, or k is equal to 10. And what about if k is equal to minus 10? Then it is going to be at, usually we write minus 180 degrees. Okay. This is for k is equal to minus 10. Plus 180 or minus 180, it represents the same thing, right? So we take minus 180 because the phase is usually in the negative value for the minimum phase functions, for all the practical functions that we consider. Now the next kind of function that we will be discussing is poles or zeros at origin. So it might be more than one pole or zero. So that is why we take the function g of j omega, we write as j omega to the power plus or minus p. Okay, where p is the degree of root. So if there is only one root, then there is going to be p is equal to 1. If there are two number of roots, poles or zeros, then p is equal to 2. Then what about plus? Plus implies that it is a 0 at origin, and negative sign implies that it is a pole at origin. Now what is the magnitude in dB? This is going to be 20 log mod j omega to the power plus or minus p, right? So what is this going to be? P you can take outside, so plus or minus 20p log of omega. This is in dB. Okay, so we can see that the constant function, it was independent of omega, so that is why it was a straight line irrespective of omega, but now this is dependent on omega. If you compare this with the equation of straight line, what was the equation of straight line we discussed for a semi-log sheet? This is equal to y is equal to log m log x plus c. Okay, now c here is 0, y is the magnitude, log x is log omega, c is 0 here. So that means when omega is equal to 1, the magnitude is equal to 0. And what about the slope of the line? This is going to be equal to plus or minus 2p. Okay, because if you compare here, this m here is equal to plus or minus 20p. Next, what about the phase? The phase is given by angle g of j omega is equal to plus or minus p times 90 degrees, because one pole or origin, it will have a angle 90 degrees. So positive implies that it will be a 0 Negative means it is a pole. Okay. P will be the number of the poles or zeros. What is the thing that you can see here? This is independent of the frequency. So that means it is going to be a straight line irrespective of what is the value of frequency. Let us now draw the magnitude and the phase plots. First we will consider the magnitude. Once again in dB we are considering, and this is the omega function. This is on a log scale. Okay. So let us say 0 will be somewhere here. And frequency scale we will start from 0.1. Omega is equal to 0.1. Now if you take a single 0, 1 0 at origin, if you take, then what will be the value of P? This is simply going to be 1. Then what will be the magnitude at omega is equal to 0.1? That is the initial magnitude. This is going to be plus 20 into P is 1 into log 0.1. Log 0.1 will give you minus 1. So you're going to get minus 20. Let us say minus 20 is here. Okay. So this will be 1 point. Another point is when the magnitude will become 0 when omega is equal to 1 radian. Right. So if this is omega is equal to 1, then this intersection is going to be another point. Now if you join these two lines, you can just extend it. This is the magnitude plot for 1 0 at origin. Okay. So that means j omega. What about the case when there are 2 zeros at origin? Then what will happen to P? This is equal to 2, and the magnitude is simply going to be multiplied with 2 compared to the initial one, right? So this is minus 40 dB. And what about the slope? The slope is going to be plus 20p, which is going to be plus 40 dB per decade. The slope we write as dB per decade. What was the slope here? This was plus 20 dB per decade. Okay. Now if minus 40 is considered here, then from here it will reach the same point, because at omega is equal to 1, magnitude will be equal to 0 for this function as well. And then you extend it. So this is for 2 zeros, that is j omega whole square. You can write the slope as well here. This is plus 20 dB per decade and this is plus 40 dB per decade. What about the case when there is a pole at origin? One pole at origin. This will give you P is equal to 1 only, but it is going to be minus P. Okay. Then what will be the magnitude? This is going to be equal to minus 20 log 0.1, which is going to give you plus 20. Then what about the slope? The slope is going to be minus 20p, which is minus 20 dB per decade. Okay. So it is going to start from plus 20 and then it is going to reach the same point, then it is going to come down like this. So this is for one pole. That means 1 by j omega. What is the slope? It is minus 20 dB per decade. So here you can compare each of these functions. If it is a 0, then the function is going to be increasing function. If it is a pole, then it is a decreasing function, meaning that as frequency increases, the magnitude will keep reducing. And since we have taken omega is equal to 0.1, the zeros are starting from 1 0 is starting from minus 20, 2 zeros is starting from minus 40, one pole is starting from plus 20. Okay. Now what about the phase plot? The phase plot is also similarly, we will take phase on the y-axis and frequency on the x-axis. Okay. Now if it is 1 0 at origin, then what will happen to the phase? The phase is equal to plus 90 degrees, right? So let us say this is 0, then at 90 degrees you will have the phase plot of 1 0 angle j omega. Then what about if there are 2 zeros? Then it is going to be plus 180 degrees. So here also it is going to be a constant function irrespective of the frequency. Then what about if there is one pole? Then the angle is going to be at minus 90 degrees. This is the angle for phase for 1 by j omega. Okay. Similarly, if you have two poles, then it is going to be minus 180 degrees. Angle 1 by j omega whole square. Next, let us take a simple 0. That means there is only one 0. G of j omega is equal to 1 plus j omega t. This is in the time constant form. Okay. So then what will be the magnitude in dB? First we will discuss the magnitude plot and then we can discuss the phase plot. Okay. So magnitude in dB is given by 20 log mod g of j omega. This is going to be 20 log root over 1 plus omega square t square. Here what we do is we make an approximation. So what is that approximation? When omega is very small, then we take the approximation omega t is much less than 1. This will give you the magnitude is equal to 20 log 1, which is equal to 0 dB. Okay. And when omega is very large, then what will happen? Omega t will be much greater than 1, and in this case the magnitude is going to be equal to 20 log root over omega square t square, which is going to give you 20 log omega t. Okay. So this is a constant line, 0 magnitude, and this is a line of what is the slope here? It is 20 dB per decade, plus 20 dB per decade. Okay. So now we can say that for small frequencies 0 dB will be the magnitude, and for large frequency 20 log omega t will be the magnitude. So when we draw the magnitude plot, this is the magnitude axis, this is the frequency axis, mod of g of j omega in dB. Now if you draw these two plots, this is 0 dB, let us say. So this is the plot when omega is very small. And what about when omega is very large? It is a line of slope 20 dB per decade. So you can write here plus 20 dB per decade. So let us say the plot starts at omega is equal to 0.1. Then if you substitute omega is equal to 0 here, whatever will be the value, that will be the magnitude here. Okay, we are not concerned about that point right now. You can see that these two plots are intersecting at this point. Okay, this point is going to be called as the corner frequency omega c. What is the expression for this? If you equate both of them, that is 20 log 1 is equal to 20 log omega t if you do. This means that what? Omega t is equal to 1. So omega is equal to 1 by t. This is at the corner frequency, that is when omega is omega c. Okay. So omega c you can write as 1 by t. At 1 by t both the plots are intersecting. Okay. Now since for smaller frequencies this is the line, we take this line, and for larger frequencies this is the line, we take this line and we ignore this part. So then the plot for the simple 0 is going to be like this. This is the plot. But remember that this is an approximation only, and for this reason the straight lines are called asymptotes. The actual plot is going to look something like this. It will be initially 0, but then it will start rising, and then eventually it will meet the other asymptote. Okay. So this is the actual plot. So you can see that for the approximate plot, the magnitude at corner frequency is 0, while for the actual plot it is not 0. So let us see what is the magnitude actually. Magnitude of actual plot at corner frequency. This you can find as 20 log root over 1 plus omega square t square. So this frequency is what? Omega c. Okay. So this is going to be 20 log root 2. Why? Because omega ct is equal to 1. This you are going to get 3 dB. Okay. So that means for the actual plot, the magnitude is going to be 3 dB greater than the approximate plot. Okay. And for this reason, the corner frequency is sometimes called as the 3 dB frequency. For this reason, corner frequency is often called 3 dB frequency. Okay. Next, what about the phase? Till now we have discussed the magnitude. Now what about the phase? Angle G of j omega is equal to tan inverse omega t. So this is dependent on frequency. So once again, when omega is very small, the angle G of j omega is equal to 0 degrees, and when omega is very large, then what is going to happen? We take essentially omega is equal to infinity we take. So angle G of j omega is equal to 90 degrees. These are the limits. In between, how the plot will behave? As omega increases from 0 to infinity, the phase is also increasing. Okay. So the phase plot, you can draw something like this. This is omega. This is phase. Now let us take this to be 0 degrees and this to be 90 degrees. Okay. So initially it will start at 0, then it will start rising, and then it will reach 90 degrees. Okay. So this will be the phase plot. Next, let us consider a simple pole. That means G of j omega is equal to 1 by 1 plus j omega t. First we will consider the magnitude plot. So in fact, this is going to be almost similar to the simple 0. What is the magnitude here? Instead of plus 20 log 1 plus j omega t, we have minus 20 log 1 plus j omega t. This minus here is the only difference. Okay. So then with the same explanation, we are going to get the plot. So we can directly draw the plot. This is the frequency. Let us say we have 0 here. Then it is going to start like this. And then at corner frequency, what will be the expression for this corner frequency? It will be 1 by t. At this point, it will now start going down. Okay. Because you can in fact write down for very small omega, the magnitude is going to be minus 20 log 1, which is 0. And for very large omega, the magnitude is going to become minus 20 log omega t. Okay. So you can see that there is a negative sign here. So that means what will be the slope? The slope of this line is minus 20 dB per decade. For a simple 0, it was plus 20 dB per decade. Okay. That's all. That is the only difference. Once again, this is the approximate plot, and we call these lines as the asymptotes, and the actual plot is going to be slightly different. This is the actual plot. Once again, you can find what is the magnitude at the corner frequency for the actual plot. Okay, you are going to get minus 3 dB. Actual magnitude at corner frequency. This is going to be 20 log minus 20 log root over 1 plus omega c square t square. So this is going to be minus 20 log root 2, which is minus 3 dB. For a simple 0, it was plus 3 dB. Okay. What about the phase plot? The phase plot also, it will be almost similar only. So what will be the angle G of j omega for or at omega is equal to 0 is 0 degrees, because angle G of J omega is minus tan inverse omega t. Then what about the phase at omega is equal to infinity? This is going to be minus 90 degrees. Okay, and as omega increases, what will happen to the phase? This is going to decrease, because here you have a negative sign, minus tan inverse omega t. So you can draw the phase plot. This is the frequency axis, this is the phase. Now if this is 0 degrees, let us say this is minus 90 degrees, it is going to start like this, it is going to reduce as frequency increases, and then it is going to settle down at minus 90 degrees.